A little too many oats in your boiling water keep the flame up high. It gurgles violently, and the oatmeal is spurting, sputtering on the stove top. That's what the sun is doing, and occasionally one of these spurts. The sun is made of a charged gas. We call it a plasma in physics vernacular, and this charged gas breaks free of the surface. It spews out into space, sending a blob of plasma across interplanetary space, and occasionally one of those heads towards Earth. With the increased solar flare risk, Sunspot AR3664 has rapidly become a focal point for scientific scrutiny. This colossal sunspot, one of the most active and sizable of this solar cycle, is now at the forefront of discussions about space weather's potential impacts on Earth. In this video, we will delve into the science of this specific sunspot, explore its similarities with historic solar events like the Carrington event of 1859, and see how a similar event today could impact us. Understanding Sunspot AR3664. Sunspot AR3664 is a colossal feature on the Sun, measuring an immense 200,000 kilometers across. This makes it about 15 times wider than Earth. Its sheer size allows it to be seen with basic eclipse glasses, making it accessible for public viewing and educational outreach. This sunspot has become a significant subject for programs aiming to spark interest in solar physics and space weather among the general public. Sunspots like AR3664 are cooler areas on the Sun's surface. They form due to intense magnetic activity, which inhibits convection. This inhibition causes the area to be cooler and appear darker compared to the surrounding regions. The magnetic fields in sunspots can become twisted and sheared over time. When this happens, the tension can release suddenly, leading to solar flares. This is why deGrasse Tyson has said that the sunspot could unleash catastrophic solar storms. Solar flares are powerful bursts of radiation. AR3664 has been particularly active, producing multiple M-class and even X-class flares. These flares send bursts of electromagnetic radiation across the solar system. On Earth, these bursts can cause sudden increases in radiostatic and disruptions in communication and navigation systems. In addition to solar flares, AR3664 has been associated with several coronal mass ejections, CMEs. Coronal mass ejections occur when large bubbles of gas and magnetic fields are ejected from the Sun's corona. Depending on their trajectory, these ejections can collide with Earth's magnetic field, potentially causing geomagnetic storms. These storms can disrupt power grids and satellites, highlighting the importance of monitoring sunspots like AR3664. This is how the renowned expert explains it. deGrasse Tyson explains solar flares. deGrasse Tyson recently explained the complexities of solar flares and their potential impacts. Tyson emphasizes that the Sun is not a static ball of gas but a turbulent, active, churning entity. He compares the Sun's activity to making oatmeal that gurgles violently when overheated, describing how the Sun's charged gas or plasma can break free and spew into space. Tyson warns about the dangers of solar flares, particularly for astronauts. If you're in space when a solar flare hits, it can ionize the atoms in your body and interfere with your DNA, he explains. On Earth, we are protected by our magnetic field, which deflects these charged particles. When these particles collide with the atmosphere, they create the northern and southern lights, Tyson notes. Those are otherwise dangerous particles rendered harmless and beautiful. However, solar flares can have severe consequences for our technology. Tyson explains a large enough solar flare can change the current that moves through the grid, boosting it in some areas and reducing it in others. This can override transformers at electrical checkpoints. This has happened before and could happen again, causing power outages. Satellites are also at risk from solar flares, Tyson states. Electrically run satellites orbiting Earth are susceptible to solar flares. The more we put up in space, the more at risk our communication and space-based technology is. To mitigate this risk, scientists are developing radiation-hardened electronics that can survive these solar blasts. Tyson also points out that while solar flares are a common occurrence, our ability to monitor them has greatly improved. We have satellites looking at the Sun 24/7, giving us great images, he says. This doesn't mean the Sun is more active. It means we are better at observing and understanding its behavior. By highlighting the potential impacts of solar flares, deGrasse Tyson underscores the importance of monitoring solar activity. Understanding these phenomena is crucial, especially when considering the potential effects of a giant sunspot like AR3664. There are many methods that scientists use to keep such a close watch on these powerful sunspots. Scientific monitoring and research. Monitoring sunspots like AR3664 involves using a range of sophisticated tools and observatories. NASA's Solar Dynamics Observatory plays a critical role in this effort. The SDO provides continuous high-resolution images of the sun, allowing scientists to observe and analyze sunspot activity in detail. Ground-based solar telescopes also contribute valuable data, offering different perspectives and helping to validate space-based observations. The primary goal of studying sunspots is to understand the mechanisms behind solar flares and coronal mass ejections. By examining the growth, movement, and magnetic properties of sunspots, researchers can gain insights into the processes that lead to these solar phenomena. Understanding these mechanisms is crucial for predicting when and how solar flares and coronal mass ejections will occur. Improving predictions of space weather events is another vital objective. Accurate forecasts allow for early warnings, which can help reduce the impacts of solar activity on Earth. For instance, if scientists can predict an impending solar flare or coronal mass ejection, steps can be taken to protect satellites, power grids, and communication systems. These early warnings can prevent or minimize disruptions to critical infrastructure. Protecting critical infrastructure is a major concern in the study of sunspots. Satellites are particularly vulnerable to solar activity. High levels of electromagnetic radiation can interfere with satellite communications, navigation systems, and even cause physical damage to the satellites themselves. By monitoring sunspots and predicting solar events, measures can be implemented to shield these satellites from harmful effects. Power networks are also at risk from geomagnetic storms caused by coronal mass ejections. These storms can induce currents in power lines, potentially leading to widespread power outages and damage to electrical equipment. Understanding sunspot activity and predicting coronal mass ejections can help power companies take precautionary actions to protect the grid and maintain the stability of power supplies. There is a lot of scope for creating understanding and interest when scientists share their findings with the public. Public engagement and education. Sunspot AR3664 has become a valuable tool for educational programs aimed at teaching the public about the sun's dynamic nature and its effects on Earth. One of the most effective methods is projecting images of AR3664 for public viewing. These projections can be displayed on sidewalks, screens, or in planetariums, allowing people to observe the sunspot's evolution over time. These educational programs are designed to make solar physics accessible and engaging. By providing real-time images and updates on AR3664, educators can capture the public's interest and highlight the significance of studying sunspots. The visibility of AR3664, which can be seen with basic eclipse glasses, makes it an excellent subject for outreach activities. People can easily observe the sunspot themselves, fostering a direct connection to the science being discussed. Through these programs, the public learns about the processes that create sunspots, including the intense magnetic activity that inhibits convection on the sun's surface. This magnetic activity leads to the formation of cooler, darker areas known as sunspots. Understanding these basics helps people appreciate the complexity of solar phenomena and the importance of ongoing research. Educators also use AR3664 to explain the impacts of solar activity on Earth. By discussing how solar flares and coronal mass ejections originate from sunspots like AR3664, they can illustrate the real-world consequences of space weather. For example, solar flares can disrupt communication systems and navigation signals, while coronal mass ejections can lead to geomagnetic storms that affect power grids and satellites. Public engagement programs often incorporate interactive elements to enhance learning. These might include hands-on activities, digital simulations, and live demonstrations. For instance, participants might use simple equipment to track sunspot movements or simulate the effects of solar flares on communication devices. These interactive experiences make science tangible and memorable. In addition to live events, educational content about AR3664 is shared through various media channels, websites, social media platforms, and educational videos provide accessible resources for people to learn more about sunspots and space weather. These online materials can reach a broad audience, extending the impact of educational programs beyond physical locations. By leveraging the visibility and activity of sunspots like AR3664, educators can effectively communicate the importance of solar research. Public engagement does more than just inform. It also inspires curiosity and a deeper appreciation for the sun and its influence on our planet. But what could happen if a solar storm of this magnitude hit us today? Potential modern impacts. Modern society is highly vulnerable to solar storms due to our increased dependence on technology. A major solar storm like those produced by Sunspot AR3664 could have severe consequences. These storms can cause internet apocalypses, blackouts, and widespread disruptions to daily life. Our reliance on electronic systems and satellite communications makes us particularly susceptible to the impacts of solar activity. The potential consequences of a significant solar storm are profound. Power grids could fail regionally or even globally, leading to extensive outages. Satellite communications could be knocked offline, affecting everything from GPS navigation to television broadcasts. Beyond economic costs, there are human and environmental concerns. A prolonged blackout could compromise healthcare and access to safe drinking water. To reduce these vulnerabilities, various strategies have been developed. Hardened electrical grids and satellite shields are among the measures designed to protect critical infrastructure. Electrical grids can be fortified to withstand the effects of geomagnetic storms, reducing the risk of widespread outages. Satellites can be equipped with protective shielding to minimize damage from solar radiation. These technological adaptations are crucial for maintaining the stability and functionality of essential services during solar events. International efforts for preparedness are also crucial. Organizations like the United Nations Office for Outer Space Affairs and the International Space Weather Initiative work to enhance global collaboration and readiness. These bodies develop and promote strategies for predicting and responding to space weather events. They facilitate the sharing of information and resources among countries, helping to build a coordinated response to potential solar storms. Exercises simulating large-scale solar storms are conducted to test the resilience of national and global infrastructure. These simulations help identify weaknesses and improve response protocols. By preparing for the worst-case scenarios, governments and organizations can better protect their populations and economies from the impacts of space weather. Modern society's reliance on technology makes it highly vulnerable to solar storms like those produced by Sunspot AR3664. The potential consequences include internet apocalypses, blackouts, and widespread disruptions. Through continued vigilance and adaptation, we aim to minimize the impacts of solar activity on our technology-dependent world. The real possibility of a modern-day Carrington event raises the question: what would a modern-day Carrington event look like, and how would it affect us? To answer that, we first need to know what the Carrington event itself really was. The Carrington event of 1859 stands as the most potent geomagnetic storm ever recorded. Named after the astronomer Richard Carrington, who observed the solar flare that triggered the event, it provides a critical benchmark for understanding solar activity and its impacts on Earth. On September 1, 1859, Carrington witnessed a bright flash of light on the sun, an indication of a massive solar flare. The similarities between the Carrington event and the recent behaviors of Sunspot AR3664 are striking. Both involve intense solar activity capable of producing powerful solar flares and coronal mass ejections. The potential scale and intensity of a Carrington-like event today would be immense. Such an event would have a far-reaching impact on the global economy and daily life. Unlike in 1859, when the world was just beginning to harness electricity, today's society is deeply intertwined with technology. The consequences of a severe solar storm would be far more disruptive now due to our increased dependence on electronic systems for our economy and everyday life. The economic impact of a severe solar storm could be catastrophic. Costs could run into trillions of dollars, with long recovery times. The disruption of power grids, communication systems, and satellite operations would halt numerous industries, leading to massive economic losses. The National Academy of Sciences estimates that a significant solar storm could cost the North American economy alone trillions of dollars, with recovery spanning years. Beyond the financial implications, there are profound human and environmental aspects to consider. Critical systems like healthcare and water purification rely heavily on stable power supplies. Hospitals depend on uninterrupted electricity to run life-saving equipment such as ventilators, dialysis machines, and refrigeration for medications. A prolonged blackout could jeopardize patient care, leading to a severe health crisis. Water purification systems are also vulnerable. These systems ensure the availability of safe drinking water, and any disruption could lead to water shortages and sanitation issues. In urban areas where millions rely on centralized water supplies, this could quickly become a public health emergency. The cascading effects of a solar storm extend into everyday life. Communication networks, including mobile phones and internet services, could be severely disrupted. This would affect everything from personal communications to emergency response coordination. Financial transactions, which rely on electronic systems, could grind to a halt, impacting businesses and individuals alike. Transportation systems would also face significant challenges. GPS systems, which are crucial for navigation in aviation, maritime, and road transport, could become unreliable. This would affect commercial logistics, supply chains, and even emergency services that rely on accurate navigation data. In agriculture, disruptions to GPS technology could hinder planting and harvesting operations, affecting food supply chains. Similarly, industries that depend on satellite data for weather forecasting, like agriculture and disaster management, would find their operations severely hampered. The broader societal impact includes potential increases in social unrest and panic as people cope with prolonged outages and disruptions. The inability to communicate effectively and the uncertainty about when services will be restored can lead to widespread fear and instability. The stakes are high, and the potential consequences of inaction could be devastating for our interconnected world. History is loaded with various geostorms and other catastrophic events. Let's take a peek into what these events were and how they were dealt with. In March 1989, a severe geomagnetic storm struck Earth, causing significant disruptions. The storm began with a massive solar flare and a coronal mass ejection from the Sun. When this coronal mass ejection hit Earth's magnetic field, it triggered a geomagnetic storm that had widespread effects. One of the most notable impacts was on the power grid in Quebec, Canada. The storm induced currents in the electrical transmission lines, causing a 9-hour power outage. This blackout affected millions of people, demonstrating the vulnerability of power grids to geomagnetic storms. Satellites also experienced problems. Several satellites in orbit reported issues with their operations, including temporary losses of control and orientation. This event highlighted the risks that space weather poses to satellite communications and the importance of having resilient systems in place. The geomagnetic storm caused disruptions to communication systems on Earth. High-frequency radio communications used by airlines and maritime services experienced significant interference. This interference made it difficult for these services to operate normally, impacting travel and safety. Auroras, or northern and southern lights, were seen at much lower latitudes than usual due to the storm's intensity. People in areas like Texas and Florida witnessed these natural light displays far from the polar regions where they are typically visible. While the auroras were a spectacular sight, they were also an indication of the storm's strength and its effects on Earth's magnetic field. The March 1989 geomagnetic storm highlighted the need for better monitoring and preparedness for space weather events. It led to increased efforts to understand and predict solar activity and its impacts on Earth. Agencies like NASA and NOAA now use advanced satellites and models to monitor the Sun and provide early warnings of geomagnetic storms. The March 1989 event remains a key example of how solar activity can affect modern technology and infrastructure. But that's not all. In late October and early November 2003, a series of powerful solar flares and coronal mass ejections occurred, known as the Halloween solar storms. These events caused significant disruptions and highlighted the impact of solar activity on modern technology. The Halloween solar storms began on October 28, 2003, with a massive solar flare classified as an X17.2 flare, one of the most powerful recorded. This flare was accompanied by a coronal mass ejection that traveled at high speed towards Earth. The impact triggered a severe geomagnetic storm, leading to widespread effects. One of the immediate impacts was on satellite operations. Several satellites experienced anomalies, including temporary losses of control and orientation. The storm caused damage to electronic components and disrupted satellite communications. The Japanese ADEOS-2 satellites suffered critical failures, leading to its eventual loss. Power grids were also affected. In Sweden, the geomagnetic storm induced currents in the electrical transmission lines, causing transformers to overheat and leading to power outages. This incident showcased the vulnerability of power infrastructure to space weather events and the need for protective measures. Communication systems experienced significant disruptions. High-frequency radio communications, crucial for aviation and maritime operations, were severely affected. The storm caused widespread radio blackouts, making it difficult for pilots and ships to maintain communication, thus impacting travel and safety. Auroras were visible at much lower latitudes than usual due to the storm's intensity. People as far south as Texas and Florida observed these natural light displays. While visually stunning, the widespread auroras were a clear indication of the storm's strength and its impact on Earth's magnetic field. The Halloween solar storms led to increased efforts in space weather monitoring and prediction. Agencies like NASA and NOAA enhanced their capabilities to track solar activity and provide early warnings. This includes the use of advanced satellites and models to better understand and predict geomagnetic storms. In response to the storms, power companies began to implement measures to protect the grid. This includes designing systems to handle induced currents and developing protocols for quick response to solar events. These efforts aim to reduce the risk of power outages and other disruptions caused by space weather. The Halloween solar storms of 2003 remain a key example of how solar activity can affect modern technology and infrastructure. By studying events like these, scientists and engineers can better protect society from future space weather impacts. There's actually reports of solar storms as early as the 70s. In August 1972, a massive solar storm occurred between the Apollo 16 and Apollo 17 missions. This storm was notable for its intensity and the potential danger it posed to space missions. The event began with a series of powerful solar flares and a coronal mass ejection that traveled towards Earth. One of the most significant aspects of the August 1972 solar storm was its potential impact on human spaceflight. Had the storm occurred during an Apollo mission, the astronauts could have been exposed to lethal levels of radiation. This realization led to significant changes in space mission planning and safety protocols to protect astronauts from solar radiation. The solar storm caused disruptions to various communication systems on Earth. High-frequency radio communications experienced severe interference, impacting aviation and maritime operations and posing safety risks. Satellites in orbit were also affected by the storm. Several satellites reported issues with their operations, including temporary losses of control and orientation. This event underscored the importance of resilient systems in protecting technology from solar activity. Anomalies including temporary losses of control and orientation, the storm's radiation damaged electronic components, highlighting the vulnerability of satellite technology to space weather events. The geomagnetic storm induced by the coronal mass ejection affected power grids as well. While the storm did not cause widespread blackouts, it highlighted the potential risks that geomagnetic storms pose to electrical infrastructure. Power companies recognized the need for protective measures to prevent future disruptions. The August 1972 solar storm also had an impact on military operations. The U.S. Navy detected the storm's effects on underwater communication systems, which rely on low-frequency radio waves. The storm caused unexpected interference, prompting the military to consider the implications of space weather on defense systems. This event proved the importance of monitoring solar activity and understanding its impacts. In response, space agencies and researchers increased their efforts to study the sun and develop predictive models for solar storms. The goal was to improve early warning systems and lessen the effects of future storms on technology and infrastructure. The solar storm of August 1972 remains a key example of the challenges posed by space weather. It highlighted the need for better preparedness and protective measures for both space missions and Earth-based technology. By learning from events like these, scientists and engineers continue to improve our resilience to solar activity and ensure the safety and functionality of critical systems. In October 2003, the Anik E2 satellite experienced a significant failure due to a geomagnetic storm. This incident highlights the vulnerabilities of satellite technology to space weather events and the importance of improving resilience. The Anik E2 satellite was part of a fleet operated by Telesat Canada, providing essential communication services across North America. On October 28, 2003, a powerful solar flare erupted from the Sun, accompanied by a coronal mass ejection. This coronal mass ejection traveled towards Earth, impacting the planet's magnetic field and triggering a severe geomagnetic storm. The geomagnetic storm caused substantial anomalies in the operation of the Anik E2 satellite. The satellite experienced a loss of control, resulting in a temporary shutdown of services. Engineers worked to regain control, but the storm's impact had already caused significant disruptions. The failure of the Anik E2 satellite affected various communication services, including television broadcasts and data transmissions. In May 1967, a significant solar storm nearly triggered a U.S. military response during the Cold War. This event highlighted the potential for natural solar activity to be mistaken for hostile actions, emphasizing the importance of understanding space weather. On May 23, a large solar flare and subsequent coronal mass ejection occurred, sending a wave of charged particles towards Earth. As these particles interacted with Earth's magnetic field, they caused a geomagnetic storm that had widespread effects. One of the most immediate impacts was on the U.S. military's early warning radar systems, which experienced severe jamming and radio blackouts. At the height of the Cold War, the sudden loss of radar and communication capabilities was a serious concern. U.S. military officials initially suspected that the radar jamming was a deliberate act by the Soviet Union, potentially signaling the onset of a nuclear attack. This misunderstanding led to heightened alert levels and the preparation for possible retaliation. Fortunately, space weather forecasters at the North American Aerospace Defense Command had been monitoring solar activity and were able to quickly identify the true cause of the disruptions. They informed military officials that the radar and communication issues were due to the solar storm, not an act of war. This timely information prevented a potentially catastrophic military escalation. The May 1967 solar storm also affected other technologies. High-frequency radio communications used for long-distance communication experienced significant interference. This disrupted both civilian and military operations. Auroras were visible much further south than usual, providing a visual indicator of the storm's intensity. While these natural light displays were beautiful, they also served as a reminder of the powerful forces at play during a solar storm. In 1921, one of the most intense geomagnetic storms in recorded history occurred, known as the 1921 Railroad Storm. This event had significant impacts on communication and transportation systems, particularly affecting the railroad industry in New York. On May 13th to 15th, the storm induced electric currents in the ground and infrastructure, causing widespread disruptions. The most notable impact was on the railroad systems in New York. The induced currents caused signaling systems to fail, leading to chaos in rail operations. Telegraph and telephone lines, critical for communication at the time, were also severely affected. Many telegraph stations reported equipment failures and disruptions in service. The storm's intensity was such that telegraph wires and equipment were damaged, with reports of fires starting due to the induced electric currents. Telegraph operators received electric shocks from their equipment. The disruption of communication systems had a cascading effect on transportation and logistics, causing delays and confusion. In addition to the problems faced by the railroad industry, the geomagnetic storm affected other parts of the world. Telegraph systems in Europe and North America experienced significant disruptions as well. The 1921 railroad storm also caused spectacular auroras to be visible at much lower latitudes than usual. People in New York and other parts of the United States reported seeing vivid auroras, which were typically confined to polar regions. In April 2001, a major solar storm highlighted the vulnerability of modern technology to space weather events. This storm, one of the most significant of the early 21st century, caused widespread disruptions to GPS systems, communications, and power grids. On April 2, 2001, a powerful solar flare erupted from the Sun, followed by a coronal mass ejection. The storm reached its peak on April 6, 2001. One of the primary impacts was on GPS systems. The geomagnetic storm caused significant errors in GPS signals, affecting navigation and timing services. High-precision GPS applications, such as surveying and aviation, were particularly impacted. The storm also affected communication systems. High-frequency radio communications used by aviation and maritime industries experienced severe disruptions. In some regions, the storm induced electric currents in power lines, leading to voltage fluctuations and potential transformer damage. Thankfully, no major blackouts were reported. In February 2022, a geomagnetic storm caused by a solar flare had a significant impact on SpaceX's Starlink satellite constellation. This incident highlighted the vulnerability of satellites to space weather and the importance of designing systems to withstand such events. On February 3, 2022, SpaceX launched 49 Starlink satellites into low Earth orbit. Shortly after deployment, a geomagnetic storm struck Earth, increasing atmospheric drag on the satellites. This increased drag caused 40 of the 49 newly launched satellites to fail and burn up in the atmosphere. The satellites were unable to reach their intended orbits and were destroyed as they re-entered Earth's atmosphere. The February 2022 incident highlighted the need for improved resilience in satellite design. SpaceX and other satellite operators must consider the impacts of space weather when planning launches and satellite deployments. Thanks for exploring with us. If you enjoyed these revelations, click now on the next video that pops up on your screen. It's unbelievable.